Every T-Rex you've ever seen looks like a scaly monster. But in 2012, Chinese scientists found a 30-foot feathered tyrannosaur that could rewrite everything. And there is one problem. No Western scientist is allowed to verify the fossil. As long as the world's best feathered dinosaur is locked away, our museums keep telling an outdated story. Why is Yutyrannus huali off limits? What does this secrecy cost all of science? At nearly 9 meters long and weighing around 1.4 tons, Yutyrannus huali stands as the largest feathered dinosaur ever discovered. Its bones were first unearthed in Liaoning Province, China, from rocks dating back 125 million years ago. But it is the details preserved in the slabs that set it apart from every other tyrannosaur. 3 separate skeletons surfaced from the same quarry, 1 adult and 2 juveniles. These fossils were more than bones. They came with evidence that changed the way paleontologists think about dinosaur skin and insulation. The adult specimen stretches almost the length of a city bus, with a skull nearly 1 meter long. Scientists focused on impressions around the tail, neck, arms, pelvis, and even the feet. Embedded in the rock, filamentous structures extend up to 15 centimeters, over 6 inches, on several parts of the body. The smallest juvenile shows filaments on its arms and neck, and the adult preserves them along the tail. These are not scattered patches or decorative crests. They form a shaggy down-like covering, dense enough to suggest body-wide insulation. Xu Xing, the lead paleontologist on the discovery, described them as fuzzy down like baby chicks. In his 2012 Nature paper, Xu wrote that Yutyrannus dramatically increases the size range of dinosaurs, for which we have definite evidence of feathers. For context, before this find, the largest known feathered dinosaur was Tyrannosaurus, barely 1/40th the mass of Yutyrannus. The filaments are not just long, they are distributed across multiple body regions, preserved in slabs cut to fit through a museum door. High-resolution photographs show their orientation and density, but not their microstructure or color. Each of the 3 specimens was prepared at the Institute of Vertebrate Paleontology and Paleoanthropology in Beijing, then sent to regional museums, 1 to Zhucheng Dinosaur Museum in Shandong, and 2 to Erlian Haoti Dinosaur Museum in Inner Mongolia. The chain of custody is legal, with no evidence of smuggling or export. All 3 fossils remain in China under state protection. The numbers are clear. 3 skeletons, 1 up to 9 meters long, filaments reaching 15 centimeters, feather traces on the tail, neck, arms, pelvis, and feet. These metrics are the hard evidence, quantifiable, published, and visible in the plates. They are the foundation for every debate and every reconstruction that follows. Liaoning Province sits at the heart of a paleontological treasure trove, not because of what was found, but because of how it was preserved. The rocks here are layered with ancient volcanic ash, the result of repeated eruptions during the early Cretaceous. Each blast blanketed the landscape in fine tuff, burying animals and plants in a matter of hours, sometimes minutes. This rapid entombment created conditions almost nowhere else on Earth. Conditions that lock in not just bones, but delicate traces of skin, feathers, and even internal organs. The chemistry of the ash is key. Silica-rich volcanic dust reacts with water and organic material, forming a mineral crust that shields fossils from decay and scavengers. Over millions of years, this crust hardens, preserving soft tissues that would normally vanish. The result is a fossil record that reads more like a snapshot than a skeleton. In Liaoning, downy filaments, flight feathers, and even pigment cells survive the ages, offering direct evidence of dinosaur appearance and biology. This region's fossil beds, especially the Yixian and Jufotang formations, have produced more than 1,000 feathered dinosaur specimens. Sinosauropteryx, uncovered in 1996, was the first dinosaur anywhere confirmed to have feathers. It was a small, fox-sized predator with a tail ringed in ginger filaments. Microraptor, discovered soon after, stunned scientists with its 4 wings, flight feathers on both arms and legs. Anchiornis preserved not just feathers but color patterns, with melanosomes revealing a body striped black and white with a red crest. The diversity is staggering. Some Liaoning dinosaurs wore simple fuzz, others boasted complex asymmetrical flight feathers. There are long, ribbon-like plumes, short bristles, and forms in between. Each new slab adds to a growing archive, showing that feather evolution was messy, experimental, and far more widespread than once thought. Yutyrannus is not an outlier here. It is the largest and perhaps the most dramatic, but it stands on the shoulders of dozens of Liaoning discoveries. The same ash that locked in its 6-inch filaments also preserved the blueprints for avian flight, the palette for dinosaur color, and the mosaic of feather types that blur the line between bird and reptile. In Liaoning, the question is not just what dinosaurs looked like. It is how much of that story we are able to see thanks to a perfect storm of geology and chance. Phylogenetic bracketing is the method paleontologists use to infer missing details. Scientists compare a fossil to its closest relatives to fill in gaps. In the case of tyrannosaurs, the bracket runs from small, early species like Dilong, known for a feathered coat, up to the giant Yutyrannus, which has dense filamentous feathers across its body. T-Rex sits between them on the family tree. If both a smaller cousin and a larger cousin had feathers, it is reasonable to infer that T-Rex might have been at least partially feathered. Phylogenetic logic supports that inference. Scientists do not stop at family ties. They also look at climate. Oxygen isotope studies from fossil bones and teeth show that the Yixian Formation, where Yutyrannus was found, had an average annual temperature of 10 degrees Celsius, about 50 degrees Fahrenheit. That is cool enough that insulation would be a survival advantage, especially for juveniles or for adults during cold snaps. T-Rex lived in what is now Montana, and during the late Cretaceous that region experienced seasonal chills and likely frosts. The environment would have rewarded adaptations like feathers that help retain body heat. This combination of bracketing and climate data forms the scientific baseline for inferring feathers in T-Rex. The evidence is not based on isolated fossils alone. It is about patterns across related species and the environments they lived in. That same comparative logic has already rewritten displays for other dinosaurs. Velociraptor, once pictured as a scaly predator, is now universally shown with feathers thanks to similar fossil finds from Mongolia and China. The insulation argument gets stronger when we consider the size of Yutyrannus. Before its discovery, many researchers assumed only small dinosaurs needed feathers for warmth, because large bodies retain heat more efficiently. Yutyrannus, at over a ton, breaks that rule. Its thick feather covering suggests that even large predators benefited from insulation. If a 9-meter tyrannosaur needed a downy coat, it is harder to argue that a 12-meter T-Rex would be completely bare. Insulation becomes a plausible function even at large body sizes. This is how paleontologists build their case. They stack evidence from anatomy, climate, and evolutionary relationships. The conclusion is not that T-Rex definitely looked like a giant chick. Rather, the old image of a bare-skinned, scaly monster is no longer the only scientifically defensible option. The logic is methodical and comparative, and that is why the debate over T-Rex appearance continues to evolve, one bracket, one climate reading, one fossil at a time. Juvenile tyrannosaurs offer a rare clue in the debate over dinosaur feathers, but the evidence is incomplete without access to the most important specimens. In North America, a handful of juvenile T-Rex fossils show a bone surface texture that some paleontologists interpret as a sign of feather attachment. Tiny pits and grooves where follicles might have anchored downy coverings. These hints, visible under a microscope, have fueled speculation that at least young tyrannosaurs started life with a fuzzy coat for warmth. Yet the adult T-Rex fossils that museums display tell a different story. Skin impressions from Montana and South Dakota show pebbly, scaly patches, no feathers in sight. The sample size is small, just a few square inches, from a creature the size of a city bus. But these are the facts available for scrutiny. What is missing is a direct comparison. The Yutyrannus juveniles, preserved with filaments on their arms and necks, could bridge the gap between the patchy evidence in North America and the scaly skin impressions from adult T-Rex. But the only way to confirm whether those bone textures really indicate feathers is to examine both the fossilized bone and the attached filaments under high magnification. That means hands-on study, scanning electron microscopy, thin sections, and chemical analysis techniques that go far beyond what published photographs can provide. Dr. Thomas Holtz, a leading tyrannosaur researcher, has voiced his frustration in interviews. He says, quote, "We can see the filaments in the photos, but we cannot test their structure, their composition, or their growth. We are left guessing about the details that could settle the debate," end quote. Western paleontologists have asked for access to Yutyrannus, hoping to confirm whether the features seen in juvenile T-Rex bones truly match the feathered juveniles from Liaoning. Without the ability to compare the microtextures side by side, the scientific method stalls. The urgency goes beyond academic curiosity. Museum displays, textbooks, and public understanding all depend on what can be verified. If the Yutyrannus filaments are truly anchored in the bone in the same way as those hypothesized for T-Rex, it would mean a fundamental rewrite of what the world's most famous dinosaur looked like. But as long as the specimens remain out of reach, the strongest evidence sits behind closed doors. At the heart of the problem is verification. Photographs, even high-resolution ones, can show the presence of filaments, but not their microscopic details, or the way they connect to the bone. Color, structure, and growth patterns all remain out of view. The call from Western researchers is clear. Without access to the actual fossils, every reconstruction is provisional. The science demands confirmation, but the legal and institutional barriers keep the answers locked away. China's Cultural Relics Protection Law, in place since 1982, draws a sharp line between ordinary fossils and those considered national treasures. Fossils like Yutyrannus are not treated as scientific samples, but as state property, grouped with ancient bronzes and scrolls under the highest level of protection. Any vertebrate fossil of scientific value found on Chinese soil is automatically claimed by the state, and strict rules govern what happens next. The law sets up a two-tier system. Most fossils receive general protection, but specimens deemed exceptionally rare or important, such as Yutyrannus, are placed in a special protection category. This triggers a series of legal barriers. Local natural resources departments handle permits for routine finds. But once a fossil is classified as special protection, decisions shift to the National Ministry of Natural Resources. Here, the process becomes far more restrictive. Central to this system is the National Expert Committee on Fossils, a panel of senior paleontologists and geologists. Any request to export, loan, or conduct certain studies on a special protection fossil must go through the ministry, which forwards the application to the committee. The committee has 5 working days to review the case and issue a written opinion. In reality, their verdict is rarely in favor of export or foreign study, especially for fossils that could alter scientific understanding or attract international attention. Professor Zhou Mi, an expert in UNESCO heritage law, calls the committee a firewall. Their job is to make sure fossils of exceptional value stay under Chinese stewardship. Loans and exports are possible, but only if the scientific and cultural risks are minimal. For Yutyrannus, this means foreign researchers almost never gain access. The law requires written explanations for denials, but these are not released publicly. The result is a system where the most significant fossils remain in China, and key evidence for scientific debates is kept inaccessible. The intention is to prevent a repeat of the colonial-era artifact drain and to keep China's paleontological heritage firmly within its borders. In May 2012, U.S. authorities seized a nearly complete Tarbosaurus batar skeleton from a New York auction house. The specimen, smuggled out of Mongolia and sold for over $1 million, became the centerpiece of a courtroom battle that stretched for years. By 2015, the dealer behind the sale, Eric Prokopi, was sentenced to 3 months in prison and ordered to pay $80,000 in restitution. The dinosaur was repatriated, but the scientific loss was permanent. Key details about where and how the fossil was found were erased, and any hope of reconstructing its environment vanished with the paperwork. This is the real-world fallout of tight fossil restrictions. When legal access dries up, but global demand stays high, a black market fills the gap. Fossils move from quarry to collector, stripped of their scientific context. Every time a specimen crosses a border illegally, the chain of custody breaks, and with it, the ability to verify age, location, or authenticity. For paleontologists, a smuggled fossil is often little more than a stone curiosity, impressive but scientifically crippled. Museums face a different kind of dilemma. In the absence of direct access, curators rely on published photos and second-hand reports. The American Museum of Natural History, the Field Museum, and London's Natural History Museum still display T-Rex as a scaly giant, sometimes with a token patch of fuzz, but never fully feathered. The reason is not skepticism, it is protocol. Without the chance to examine Yutyrannus in person, to test its filaments under a microscope, or to sample its bones for isotopes, curators stick to what can be independently verified. The result is a gallery of prehistoric icons that reflect the limits of access, not the limits of evidence. There is a way forward. Some experts propose on-site research teams, international scientists working alongside Chinese colleagues, using mobile labs to conduct CT scans, microscopy, and non-destructive tests without moving the specimens. The fossils stay in China. The data travels. This compromise preserves national heritage while letting global science advance. It is not perfect, but it is a start, a policy that could keep fossils out of the black market and put the truth back in the hands of those who study it. Today, the world's largest feathered tyrannosaur sits sealed behind museum doors, its secrets off-limits and its evidence debated but not examined. As fossil nationalism hardens, our picture of prehistory becomes a product of politics as much as science. The truth about T-Rex may be written in stone, but who gets to read it still shapes what we all believe. What's your take? Science without borders or heritage without compromise?